All right, so for week two's class, we are going to be looking at sequences, series, and binary operations. So the objectives for this lesson are as follows. So by the end of the lecture, we are going to be able to understand different types of sequence and series types, calculate their sums and determine convergences of GPs, and then understand and apply binary operations, including identity and inverse. So of course, we're going to be looking at arithmetic progressions, geometric progressions, and harmonic progressions, which are under sequence and series, and then binary operations and their relevant terminologies and how they are applied. So this is what this lesson is meant to cover, and hopefully at the end, when I've gone through the slides from the beginning to the end, you should be able to have a good enough understanding of this. And of course, if there are any issues, there's always room for questions as well at the end. So we'll get right into it, and we'll be starting off with arithmetic progression. So this is a sequence in a sense. And so what an arithmetic progression is a sequence with a constant difference between the terms. Now, in layman's English, it simply means that you have a sequence. So when we say a sequence, like it's a train of numbers, a continuous train of numbers, right? That's a sequence, like a line, and then you just have a number, number after it. Now, for an arithmetic progression, there is a pattern. Sorry, there is a pattern that sequence follows, right? So there is a way to be able to know what comes next in that sequence. And of course, we can know this when we have maybe the first 3 or 4 terms of the sequence and then identify that pattern. But then, specifically speaking, for an arithmetic progression, it always has a constant difference between the terms. So what's the difference? The difference is subtracting the last number from the next number. That's difference. So in math, when we say difference, we mean the product of a subtraction, right? And so to just illustrate that, we have something like this: 2, 5, 8, and 11. Now, I can comfortably tell you that this is an arithmetic progression. And why is that the case? Because I see that between 2 and 5, the difference between that's 3, right? And so I'm going to need that to hold for the next couple of numbers before I can conclude that this is an arithmetic progression. And so I check the next one. Between 5 and 8, which is the next number in this sequence, the difference is also 3. Wonderful. So let's check the next one, just to be sure. 8 and 11, the difference is also 3. So a pattern is clearly showing itself here that we have a constant difference between the terms in this sequence. So the difference between 2 and 5 is 3. 5 and 8 is 3. 8 and 11 is also 3. And so we can say that this is an arithmetic progression because the terms have a constant difference, which in this case is 3. And of course, this is presented by D. So that difference is denoted by D. And then the A that you have here is used to represent the first 10 of that sequence, of that AP. So this A and D are important because it's what you use to determine subsequent members of that arithmetic progression. And so the AP takes the general form, which is written out here. So the first term is usually A, like I've explained, which is 2 in this case. And then your second term is what? A plus D, right? So you are adding it because that 3, now that D is your difference. And so to get the next term, you add that difference to your previous term. So if the second term is A plus D, the third term will be A plus D again, right? And algebra, that's A plus 2D. So we are seeing that the first term is A, the second term is A plus D, the third term is A plus 2D. Now, if I were to continue this further, my fourth term will be A plus DDD, which is 3D. My fifth term will be A plus D plus D plus D up to 4D. So as I was saying, we're looking at arithmetic progressions, and then we are talking about finding the n term of an AP formula, and then we're also looking at finding the sum of an AP with the formula as well. Of course, doing this manually by hand will be too cumbersome, and so it's important that you keep these formulas in mind. So this is for the sum of an AP. So for the sum of whatever terms you need to calculate, n becomes, so for example, the sum of the first 10 terms. So n becomes 10. A is your first term and D is your common difference, which you should know from the given sequence. And then you just put it into the formula and then you arrive at your answer. So that's that for an arithmetic progression. So we move on now to the next slide, which is geometric progressions. Now, for arithmetic progressions, the sequence follows a pattern where the difference between the term and the next term is constant. So it's an addition difference. Now for geometric progressions, it also has a sequence and follows the pattern. For now, the difference is in multiplication, a product, and not a difference. Unintended. But anyway, so I'll just list an example. So when we're talking about arithmetic progressions, our constant difference t was used to get the next step. So we would have this plus this is going to be the next step. But for geometric progression, it's the multiplication. And so the first term a still remains the same. But now instead of having d, we have r, where r is referred to as a common ratio. Now r in this example here is 2. Because if you look at this GP, 3 times 2 gives you 6. 6 times 2 gives you 12. 12 times 2 gives you 24. And so on and so on and so forth. So we're going to continue this GP. The next step would be 24 times 2, which will give us 48. And then continue on to give us 96. And then continue on to give us 190 something. So on and so forth. So here it's a multiplication that follows. And of course, the general form. So for an AP, we had a plus d and a plus 2d and a plus 3d. Now for each GP, it's the same multiplication. We're going to have a, our first step. And the next step will be what? A times r, which is ar. And the next step will be a times r, which is a times r squared, which is ar squared. And so our third term is ar squared, our fourth term is ar cubed, our fifth term is ar to the power 4. And so we see a pattern like 4, where the nth term is going to be the power of r is going to be 1 less than the nth term. And so to find the nth term of our geometry, we arrive at the general formula where T of n is equal to ar raised to the power n minus 1. So of course, this formula helps out, especially when we want to find larger sequences, larger GPs. So for example, for this particular one, we have the first 4 terms. If someone were to ask you to find 10th term of this, instead of writing out 3, 6, 12, 24, 48, so you get 10, you could simply just plug it into this formula, right? And so your 10th term will be a times r raised to the power 10 minus 1, a times r raised to the power 9. And of course, knowing a and knowing r, you can simply follow them to the formula, arrive at your answer for a for 10th term. So general formula for n term is a r raised to the power n minus 1. Now, likewise, if we had a formula for sum of it, also here have a formula for sum of a GP, right? So now there's a slight difference here because we have a fraction, and I'll become apparent why that difference is necessary. Or slide. So it's in the formula. Now for the sum of a GP, formula is as follows: a into 1 minus r to the power n all over 1 minus r, where r is not equal to 1. Now this condition is important because the denominator of this formula is a fraction. It's a 1 minus r. Now if r were to be 1 and you put in r here, you have 1 minus 1 and you have 0. Now if you're dealing with fractions, we know that if your denominator is 0, then you have an undefined fraction. Because you cannot, there's nothing that is expressed like 0. So we have a set coefficient for the formula to work. And of course, if you think about it in context of an example, let's say you had each, you're the first test. Right? If your r was 1, it would mean that the next step is times 1, which is 2. And then the next term will be 2 times 1 again, which is 2. And the next term is 2. And so this does not actually represent any sequence or any series. You're simply fixing the same amount of time. And so you would never have a case where your common ratio is 1 because it doesn't actually result in GP. So hence the condition that R is not equal to 1. Now, there is a second formula underneath where conditions that actually matter are stated. So the first formula applies for the case where R is less than 1. So where your common ratio is any fraction or decimal less than 1, and of course that is applicable, that can happen, right? So if your common ratio is half, for example, 2 times half is 1, 1 times half is 0.5, 0.5 times half is 0.25, like that. 1 over 8 is 0.125. So here we see that sequence is actually decreasing because the common ratio that we started with, the common ratio that we have is less than 1. Now, if the common ratio is greater than 1, so like in the previous example, C, where the common ratio is so we have something A, but in this case, where we have R, this is the first step, and then continues. However, even when your R is a fraction, it's still possible to find this negative. So the only difference in the formulas is that the positions of 1 and R are switched. For the case where R is less than 1, the formula is 1 minus R to the power n over 1 minus R plus times A. For the situations where R is greater than 1, from this R to the power n minus 1 over R minus 1. Now, either formula can actually work for either case, actually, as we'll see this example. But it is just fitting to use because, of course, they are different. So we now have to get into convergence and divergence geometrical progressions, which is beyond the scope of this lecture series. But then, just to be safe, if R is less than 1, apply this, and if R is greater than 1, apply this. So that is as straightforward as it goes. And then we have an example here. So we have the same GP that we had in the previous slide, and we asked to find the sum of the first 4 terms. And here to sum this up by hand, it should be 3 plus 6, which is 9, plus 12 to 1 plus 4, which is 45. But then you should plug them into the formula. So we have A, which is 3, into 1 minus R to the power n. Now R is 2, so 2 to the power of 4 is 16 over 1 minus R, and our R is 2. So now in this example, the formula that was applied to the first one, right? But ideally, you should use the second one because our R2 is greater than 1. And if you were to use the second one, you would still arrive at the same answer because the only thing that would change would be that our R minus 1 is going to give us a positive answer, and Rn minus 1 is going to give us a positive answer. Here we have a negative answer in the bracket and a negative answer because it still cancels out positive result. So which is 5 as well. So you have 3 times 16 minus 1 over 1. 3 times 16 equals 5. The answers are the same. Of course, it's fitting to use a formula that is appropriate for whichever situation you find yourself. So these are the formulas for relating the sum with geometrical progression that should be up until a certain number of them, S of n. Now, we've spoken about finding the sum up until a certain number of terms. For a geometrical progression, and also want to find the sum. So like I said, the series, sequences of series go on forever to infinity, right? But then you cannot physically sum up your numbers until infinity. But there are cases that we arrive when you want to know, okay, when this series ends, what is the actual sum? And we have a formula for calculating that, right? And then formula is A over 1 minus R, where R is less, where absolute value of R is less than 1. So if, for example, in this situation now we have A as 5 and R as half. So plugging it into this formula, 1 minus half is half, and 5 over half is 10. Now, if, for example, we have to ask to find the sum of this GP to infinity, so 3, try that out, 6, 0, 4, plus, and we want to find the sum of this GP to infinity. We will simply apply the same formula, right? So our first term, our A in this case, is 3. And our common ratio is 2. R. So putting this into this formula, we'll have that A, which is 3, all over 1 minus 2. That will be 3 over 1 minus 2, which is minus 4. And that will be 3 over minus 1, which is minus 3. Now we have a negative number for a sum up until infinity. However, which is why this condition says that the absolute value of R has to be less than 1, right? So I have to now get into a distinction between divergent series and convergent series, because for a series that is convergent, it means that the series continues up until the point where it meets. But for a divergent series does not converge, does not meet again. And so since we have a negative number as our answer here, we can see that this series is divergent, because if the series were to converge, you would meet at a point and then you can sum up all the numbers to that point. However, for a divergent series, it continues to expand and expand, just like parallel lines that happen. And so there is no sum. You can have a sum of all number just for the number. So the formula specifies that this is only applicable where absolute value of R is less than 1. Here we had a situation where R was greater than 1, and so which is why we had a negative number. So it's important to also take into this condition when we are solving for sum to infinity of the geometrical progression. It's actually important. So the next one we're going to look at is the harmonic progression. So this is very similar to arithmetic progression, with only a slight difference. And the difference between this and an AP is that for a harmonic progression, you work with reciprocals. So basically, 1 over whatever you have in the AP. So we have an AP where the common ratio is 1. The difference now, so AP difference is 1. Instead of having 1, 2, 3, 4, 5, 6, 7, right? You would now have 1 over 1, which is 1, 1 over 2, and that. So it's like an inversion, an inverse of an arithmetic progression, where every other thing still applies. But then it's just that you now have the same reciprocals. And that's the same as the difference in harmonic progression. So moving on to the next slide now, we are going to go into the next part, binary equation. Now, binary operations, this is like an extension of what set theory entails actually, because we are working with operations under a particular set. So what a binary operation is actually is combining two elements in a set, give you another element that's still in that set. So for example, last week we looked at the set of real numbers, right? And for the set of real numbers, if you perform any operation, it's specifically a binary operation with two real numbers, if it gives you your answer as another real number, then that's a binary operation. And so examples of that are plus, addition, multiplication, maximum, minimum, such and such, and likewise. When we look at the examples, it's become much clearer. But then basically, it's the notation representation for a binary operation is usually asterisk symbol, like we have here. And so they can come in the operations themselves that are represented by the asterisks are varying. They can be manipulated in any way possible, but then the operation specifically like this. For example, if I have two elements, A and B, the binary operation I want to come to A and B represented by A asterisk B, right? And then actual operation I want to now write will not be written out. But then the operation itself is the fact that I'm performing an operation is represented by the asterisk symbol in between A and B. So I can say that the operation I want to perform is an addition operation of the A and B. And so A asterisk B represents A plus B. Right? I can say that the operation I want to perform is a multiplication, and then it's represented by A. I can also manipulate any other way I want. I can say this stands for AB plus 2A plus 3. But the important thing to note is that this manipulation, this representation, notation for it is represented by this asterisk symbol. And then I can now write out any form of any combination of equations that my asterisk symbol represents. And of course, it's a binary operation because whenever I finish, the answer to this my binary operation will still lie in the universal set where A and B are present. So, in binary operations, we have three properties, right? And we're going to be looking at two very important ones, which are the identity elements and class elements. So, what's the identity element? So, well, the identity element is given a non-empty set which is closed under a binary operation. So what does that mean when they say a set is closed under a binary operation? It means that if you have a set, right, and you have, so first of all, it's a non-empty set. It means that the set has elements. So it does not apply if the set is empty. So the set has elements. Now, for a set to be closed under a binary operation, it means that if I perform this operation with elements of the set, I should not get any results that is of which that answer is outside the set. So it's a closure property that if I perform an operation, so let's say I do this and I do this, A is in set of V and B in set of V, and I perform this operation, this binary operation, A after XP, and I get an answer that is outside, that's not in the set of V. It means that this operation is not closed under the set of V, right? But for it to be closed, for the set to have, for this operation to have the closure property, it means that no matter the two elements I pick from that set, whatever operation I perform, my answer is always going to be a single. So that's what a set closed under a binary operation, right? So those are the two conditions. So the set has to be a non-empty set, and then the set has to be closed for that operation, for that binary operation. So basically, the identity element is an element in that set such that if you perform an operation A asterisk E, so P now represents the identity element. In the operation A asterisk E, because B asterisk A is equals A for all E. So this is like this symbol represents that E is a member of the set, right? So the identity element is saying if you an operation any member of that set, so any element or member of that set having a binary operation of the identity element, we are going to arrive at the original answer, the original element of that set. So A asterisk E is going to be equal to A. This is, and of course, it's only going to, this is a unique element, right? There's only going to be one identity element for a given binary operation in the set. And so, for example, for addition, 0 is the identity because A plus 0 is always going to be A. No matter the number, no matter what A is, anything plus 0. And this is a simple addition. But then for each binary operation that has its own peculiar manipulations, you are going to have to determine, okay, what is the identity element for this and what's the identity element for this. So this is just an illustration to show what it means for an element to be an identity element. That if you perform an operation between any member of that set and the identity element in the binary operation, your answer should remember that same element or member of that set. So an example will probably illustrate and make it much clearer. So we have the operation here, and it is defined by this. So of course, the binary operation presented by this asterisk symbol can now be any different manipulation of the numbers, but then it will be defined for you. So the operation on the set R, so we're working with the numbers R, defined by A asterisk is equal to 2A minus 1 all over 2A. We're asked to find the identity element. Now, when we define the identity element, remember what we said that A asterisk E is equal to B asterisk A is equal to A. So in order to determine the identity element, we are going to have to replace B with E, which is our identity element, which is simple identity element. And we know that A asterisk E is equal to B asterisk A is equal to A. Now, for the expression A asterisk B, you see that this is the This is the representation. And now we're replacing B here with E. So it means that in this other expression on the right hand side, anywhere that you see, we're going to substitute and put E. Now A asterisk E therefore is equal to 2A minus 1 all over 2 plus A. I remember for identity elements, it is equal to A. Right, so we can easily eliminate what we have here and then now work with this in order to find, because the aim of this is to find the identity elements E, right? And so since we have the fraction over 2 here, you multiply 2 by 2, I going to have 2A minus 1. This becomes 2E and this becomes 2A. So we take all the A's to one side and take the E to one side. So it's going to be 2A. This one comes over to the right hand side. It takes up the negative sign minus 2A. And then 1 comes over to the right hand side as well, plus 1. So 2A cancels out 2A. Now all we have is 2E is equal to 1. And then E is equal to half. Now what this means that the identity element for this operation, A asterisk B, as has been given to us, is half, meaning that if you take out any number in the set of real numbers R, and perform this binary operation, the identity element half, you are always going to get that same element. Now, let's just test it out to confirm that what we have said is correct. So, set of real numbers, any random number, 10 is real number, right? So if I were to do 10 asterisks, our identity element is half. So if I were to put 10 here, 2 times 10 is 40. 20 minus 1. 2 times 10, 20 minus 1, 19. Right? And then 19 over 2, which is 9.5. Then plus. So now we're replacing this B with half. 9.5 plus half, which is 10. So that operation has given me my original element of the set, which is 10. Let's do an example, just to be sure that our theory actually works. If I were to put 5, 2 times 5 is going to give me 10. Then minus 1 is going to give me 9 over 2, 4.5 plus E now, which is the identity element, which is half, is going to give me 5. So you see that for this operation, A has to be one set of real numbers. Any single number that I pick and upon this operation of the identity element is going to give me the same element of that security element. And that's the property of the identity element. That if you perform the operation with the identity element, you're going to get the same answer, the same number of that set with A. So we've proven that the identity element for this operation on the set is actually half. So the next thing I would have to consider is inverse element of B. So it's kind of similar, and of course it takes from the identity. So it says that if A is a member of the set S, so we're using S as a percent, and there's an element A inverse. A inverse is inverse of A. If A asterisk A inverse is equal to the identity element. Now, so this is the condition for the inverse, that A asterisk A inverse is our inverse is going to give us the identity element. So just as an illustration, when we have the addition case, the inverse is what is similar for addition, the identity element is 0. So what is the inverse? The inverse is whatever you're going to perform an addition to 0. And so for addition, inverse of A is minus A. So again, another example to show that point. So like I said before, when you know, since the condition for an inverse element states that A asterisk A inverse is to the identity, you first of all need to have the identity element, which you know what it is, and then we find the inverse element. For this example, we've already told what the inverse the identity element is. The identity element is 0. Now we are asked to find the inverse element. So the operation is find a set of real numbers x asterisk y is x plus y minus 2xy. That's written out here. So now what you do to find the inverse element is you replace y with x inverse, which is what you're looking for. And so if you do that on the left hand side, you're going to replace y with x inverse everywhere on the right hand side as well. And so if you do that, you're going to have, so first of all, we know that x asterisk x inverse is going to give us e and e 0. So replacing y with x inverse, we have x because x inverse times 2x times x inverse, which is what you have here. And that's equal to our next element, which you have to do with 0. So this is here. Now, collect like terms as usual. So anything that has x inverse on one side and anything that does not have that on the other side. So x goes over to this other side, becomes minus x. We factorize out x inverse from here, which is 1 minus 2x. And then x inverse is simply minus x all over 1 minus 2x. So this is our inverse element. And of course, it's dependent on whatever x is going to